Hello, folks. Ooh. Somebody complained about the volume on the YouTube video being too low, so I'm trying a different microphone. Okay, let's pick up where we left off last time. We studied conditional probability, and we quickly moved into Bayes' rule, and we did an example of a medical diagnosis exam where a person was either HIV positive or not. So let me just scroll back to that example, in the sample space for that example. So a person is either HIV positive with probability 5%, or HIV not infected or not infected. So that's the actual status. And then we run an exam. This exam has probability of correct detection of 99%, meaning that if a person is indeed HIV infected, the test will declare that person as infected with probability 0.99. Otherwise, it will, with an miss error rate of 1%, will declare the person as clear. And on the other hand, if the person is not infected, the test declares that person as infected with probability 10%. Otherwise, it will correctly reject. So let's actually give the other terms their due names. So this is correct detection, and this is correct rejection. And this terminology is reasonably common and well understood. Okay, so we ended up seeing a pretty atrocious number at the end. The number that we ended up at was this very disturbing 0.34, meaning that a person has been diagnosed, has been declared by the test as being infected with HIV. What's the probability that that person actually is infected? And that number turned out to be 0.34. And that should be quite disturbing. So why is it that this is happening? I want to start off from there. Let's look at the denominator here. Let me go back to my, let's do blue this one. Let's go back to the denominator. So in the numerator, we have the probability of D and H, which we computed to be 0.0495. And in the denominator, I can also, how can I rewrite this? Well, actually, we've written it here. The probability of D is the probability of D and H plus the probability of D and H complement. What principle am I using here? The what? I can't hear you. Law of total probability. Thank you. If you're not so if I can't hear you here, then you're not going to be able to hear me on the YouTube video. So that's how it's going to work from now on. All right. Now, if I plug in the numbers here, so what was this? This number is the same as the numerator, 0.0495. And what was this number? 0.095. This is the problem right here. The probability of false alarm is too high. False alarm probability. Too high. So how should we fix this? Suppose you're a politician. You know, politicians went in Sacramento and said, hey, car manufacturers, you got to adhere to certain standards for emissions. If you were a politician working on policy for this, what would you tell the test makers? What do they have to fix? Yeah, Jack. Yeah, this is too high. So they've got to fix that problem. So How about we double the accuracy there? Well, let's see. It turns out to be correct. Yeah, that's right. It's still going to be quite high. But let's see what happens if I improve my false alarm probability. So make this 0.05. Actually, you want to make it 0.01? Okay, let's do 0.01. Jack says 0.01, we'll do it 0.01. So here we go. Let's redraw the tree. So we've got a person is infected or not infected, infected with probability 0.05, not infected with probability 0.95. And then the test will declare the person as infected with probability 0.99 and otherwise 0.01. And we have a symmetric situation at the bottom. So the miss probability is now 0.01 and this one is 0.99. Happy? So this is miss. This is false alarm. And what I'm interested in is this probability. So, probability that a person is actually infected given that the test says they're infected. And using Bayes' rule, we found that this is the probability of what? Given what? Everybody. D given, that's not everybody, that's just one person speaking on behalf of everybody. Listen, if you don't speak, somebody else is going to speak on your behalf. This is a good piece of advice to keep in mind. It works against you in real world as well. So speak for yourself. P of D given H times what? P of H. Yes. There we go. School spirit. CS18 spirit. I know you're all dispirited by this time of the semester. I'm trying to pick up some momentum here. All right. What is P of D given H? 0.99. Can you tell me which branch that is? Top one. This is P of D given H. That's how you read these diagrams. That's how you label these diagrams. Okay. So that's 0.99 times the probability of H, which is 0.05, we said, divided by the probability of D. What terminal nodes correspond to D? First one and third one. This one and this one. And so the probability of D now is, you just follow the branches now. Okay, so to get to this D right here, I just follow the probabilities of on the branches leading to that leaf, and multiply them. 0.05 times 0.99 plus what? 0.95. Now I have to follow this branch. So these are the two branches I follow. So I have 0.95 times 0.01. Can somebody compute this? Since I had prepared this for 0.05, I didn't work out the numbers here. Come on, get out of Facebook and get to your calculator and give me a number. What's the number? The top is the same as before. 0.044 what? For what? 495. 495. And this one is 0.0495. 495 plus what? 0095. And that gives me what? 84%. Is that good enough? If that test came for you, would that be good enough? That means what? What's the probability that you're actually not infected? Huh? 16%. Is that good? If you had a test done, and the test came positive, and it's the super-duper test that misses only 1% of the time, and it comes positive, and you are 16% likely to not be infected despite what the test says, how would you feel? Good? I need to walk you to the other side of campus today. So, I wouldn't feel good. There is a great book I want to introduce you to. It's called The Drunkard's Walk. It's written by a former Caltech professor. I think there's a subtitle to it as well. It's called How Randomness Rules Our World or something like that. The authors, so let me just put that as an aside. You get a lot of culture here too, hopefully. The Drunkard's Walk. And the author's name is Mlodinow. Former Caltech, I think, physics professor. Left his tenured position to go into acting. And one of his fantastic talents is writing extremely engaging books. There's a whole chapter about what we're discussing right now. Positive fallacies and fallacies of false positives. And he actually has a story, autobiographical portion in that segment, where in the late 1980s, he and his wife had applied for insurance. I guess it was life insurance. He doesn't say it, but I assume it's life insurance. And they were turned down. And the two letters they got, rejection letters, his wife's only had two words more than one word more than his letter. So his letter said, because of your test results, and his wife's rejection letter said, because of your husband's test results, we cannot insure you. And it turned out that the blood test had declared the author HIV positive. Now you got to take yourself back to the you can't take yourself back to the 1980s. I can. In the 1980s, HIV was essentially a death sentence. So needless to say, he did not have a very good time. He says, I didn't go to Disneyland that weekend. This is precisely the kind of scenario we're talking about. Notice, compare this with the probability of D given H. What was that number? 0.99, correct? So the probability that the test declares you as positive is very high, but the probability that you're actually infected, given that the test declares you positive, is much lower. I mean, this is a significant statistical difference. We make this kind of error all the time in real life. I can change the context to the following. The probability, I send my friend an email. I get no reply. I leave him a message. I get no reply. I know that if I'm out of favor with my friend, the likelihood that I get no reply is high. You agree with that? If I've fallen out of favor, let's forget my friend. I write to my boss. I write an email to my boss, I don't hear back. Okay? I know that if I have fallen out of favor with my boss, the likelihood that he's not going to or she's not going to answer my email is high. This we can all agree on, I hope. Huh? Can I see some nods? Okay. But what do I actually do in my mental processing? I have received no reply to my message. So I assume I've fallen out of favor. In other words, I assume this is high. You see the problem? We do this every day. I have received no reply from my boss, so I assume I must have done something wrong. I must have fallen out of favor. I don't think about all the other gazillion possibilities why my boss is not answering. Somebody you love died. You got into an accident. He's just sick at home. I don't know. It could be a gazillion different reasons. But we mix these two conditional probabilities every single time. And hopefully, after this course, you will slap yourself in the face every time you're about to make that mistake and say, Babak said, I should be watchful. What a violent instructor you've got. Okay. There is another way to fix this problem, which is to, even with the original statistics of the test, which is to actually run the test, run independent iterations of the test. So you can run the test twice and then say, I will declare the person as HIV infected only if both tests come positive. So let's see what happens if I do that. So now I'm going to say run the original test. Actually, let me see. Just so I don't have to rely on you computing. Let me see which. Yeah, run the original test twice. But twice independently. So the result of the first test does not influence the result of the second test. Run the original test twice. Let's see what happens. How do I draw? So can you talk to your neighbors and draw the sample space for this? Tell me how many sample points it has. Put all the probabilities on the various branches and see what you have. Once you have the diagram, then we'll reconvene and we'll do some of the calculations together, okay? So if you don't know who's sitting next to you, if it's a new person, please introduce yourselves, get to know each other, chat away, and draw. That's the book. Very much worth the read. It actually starts off with a lottery winner in Spain, I think in the early 2000s, who was asked what the secret was to picking the right number. He said, well, I dreamt of the number 7 for 7 nights in a row. 7 times 7 is 48, so I picked 48 as the last 2 digits of my number. Very entertaining author. Okay. Let's resume. So, I think we're at a point now where I can ask for a point person to be the first person to be picked every single lecture. Is anybody comfortable doing that? Brave man. Your name is? Rohan? Okay. So, were you here when I explained what it involves if, you're not here on a particular lecture? The entire class of, 800 some odd students will know. Okay. So, in exchange to you being the first person, and also you have to pick loudly, and you have to be brave enough to pick somebody. You're up for it? Awesome. So, what do you want to do? You want to take the question or pass the question? Pass the, something must have happened between these two. What's your name? Saurav? Go for it, Saurav. So, what was the question? After all this time, you're asking if Romeo was a man or a woman. Help me draw the sample space. Twice. Loud. Okay, you either are H or H complement. Probabilities are the same as before, so 0.05, 0.95, okay? So I have a declared positive or not declared, but now we're running the test twice, so I have to distinguish the results of the first test from the second test. D1 or D1 complement, okay? Okay, and the probability here was what? 0.99, 0.01. Remember, we're going back to the original test. Okay, so we have a 10% false alarm probability, and we've got a 90% correct rejection probability. Now what? So for every one of these terminal nodes, we have another test that's conducted, and we specify that with a subscript 2. So test 2 will declare the person is HIV infected or not. And let's do that for every branch. So how many possible outcomes do we have, Saurav? 8. D2, D2 complement, D2, D2 complement. And each of these, of course, is again 0.99, 0.01, 0.99, 0.01. Remember, we're in the top half. So the person is actually infected, and we know that the test will declare that person is infected with probability 0.99. And now we go to the bottom half of the graph, the sample space here. So the person is not infected, and the probabilities there are 0.1 and 0.9. Okay. So now we're saying that the person is... So what is the probability that we're after now, Saurav? Probability of... Well, no. So in the first case, we had the what was it that we computed the first time? I run a test, the test comes positive. So I get a D. What conditional probability did I compute? Probability of D given H or H given D? But D given H is already given to you in the H given the probability that the person is actually infected given a positive test result. But now we're after that probability when I have 2 positive test results. That's the probability I'm after. Hopefully this will be high. How do we compute this? This is equal to what? Let me go, well actually no, I want to keep it in the same screen. So this is equal to what over what? Loud, loud. Those guys can't hear you. Yeah, but just do it more simply. Probability of A given B is the probability of A and B divided by probability of B, right? So do the intersection. H, and because that's this intersection, I can actually put my finger on one of the nodes on the graph, right? Probability of H and D1 and D2. Which node is that? Which one? Top one. This one. That's what's in the numerator. Huh? Divided by what? Probability of? Can you sitting around him hear him? Because I can't hear him. Oh, sorry. So that's a different story. He can't speak. Why did you pick him if you know he's sick, man? Sheesh. So can you help me highlight? Rohan, you're on the hook for the rest of it. Penalty for cruelty. So, show me where to highlight D1 and D2. Yeah. Top node. Fifth node, so the fourth from the bottom, this one, right? These two correspond to the outcomes where both tests are positive. All right, cool. So I want everybody to regroup and go back to their groups and give me the numbers. What's the number at the top? What do I have to multiply? Everybody. 0.05 times 0.99 times 0.99. And in the denominator, the same thing will appear. So whatever that is will appear here as well as the first term. Because now in the denominator, I have to compute the probabilities of two terminal nodes. These two. Huh? So what do I get? What's the next part? 0.95 times 0.01, which is 0.1 squared. So what is that number? Actually, that didn't require regrouping. What's that number? Can somebody tell me? 0.837. So without having to redesign the test and make its false alarm probability twice as accurate, by simply running the test twice, we got almost the same result as what that redesign would have required. Now, if I were to redesign the test, if you want to improve on this still, what would you do? Without having to redesign the test? Run it a third time. Huh? Now, if we redesign, so this is still not good, but that's not the point. The point is that without redesigning the test, by simply running it again independently, I improved my results significantly. I went from 34% up to 84%, almost. Huh? So if we redesign the test, so that the probability of a false alarm is 0.01. I'm not going to go through all the numbers again, but if we redesign it so that it actually is 0.01, and I run the test twice, notice when we ran it once, we got this answer. run the test twice, then the probability of the person being infected given D1 and D2 jumps to a whopping 99.8%. That's pretty good. Yeah. So the question was, how do we determine if a test is good enough? You have to look at your prior probabilities. When I look at the prior probabilities that I ascribe to this model, and I just came up with that number. I have no idea what the HIV rate is in the general population. I guess there are people who know that answer. But I just assumed it was 5%. 5% and 10% probability of false alarm. Look at how, in fact, the false alarm rate is double the fraction of the population that's theoretically, at least presumably, sick or infected. What I want is those error probabilities to be much smaller than the prior probabilities of infection or non-infection. That's really what messed us up in the original setup. And you can compensate for that with repeated experiments, with repeated exams. Okay? By the way, the error that the kind of mixing up of the conditional probabilities, of probability of A given B versus the probability of B given A that we make in our daily lives, physicians make very often, both in doing research in biomedicine and also in discussing diagnoses with their patients. So we've got to be very careful. In fact, there's a Stanford professor who his last name is Ioannidis. Before he joined Stanford, I think he was at Columbia, and he wrote a paper called "Why All Research Results Are Wrong." He's talking about biomedical research. He has a whole paper on this. It's a serious problem. When you want to do clinical trials, so a particular drug worked on 45 out of 70 patients, what can you conclude about the next person who comes and is treated with that drug? How big should your sample space be? What can you conclude and what can you not conclude? These are all the issues that come up in applying the theorem of Bayes. Ron, you have the question? I can't hear you. More about the? Uh-huh. Yeah. So you have a gazillion different test kits that have been produced. Maybe some test kits have been produced using the same manufacturing process in the same plant on the same day, and something went wrong on that day. Then you have, obviously, associations between the particular packages of the exams that came out that particular day. This happens with food as well. Suddenly, meat that shows up in a particular store has infections, and they recall the meat and they try to trace where it came from. They even do it with Manuka honey in Britain. Manuka honey is a pretty sophisticated honey with lots of medicinal properties. They use it in Britain in some surgeries even. They put it instead of antibacterial material on stents and things like that when they want to enter the body. So for those, they actually have serial numbers for the batches that come from particular locations. But we're dealing with simplified models here, right? So we're just going to assume we have two different test packets run by different people at different times. So it's reasonable to assume that they lead to independent results, but they follow the same statistics, so that they have been designed with the same parameters: a correct detection probability of 99%, a false alarm probability of no greater than 10%. Okay. All right. I saw some more hands. Jack. Yeah, so that's the probability of the miss. That's exactly what we had. Let's go back to the original one single test situation. The question is, what happens if somebody is actually has the infection, but the test declares, wait a minute. Oh, yeah, so that's the miss probability. That's this one. Yeah, that is so there are two kinds of errors that can occur, right? And they have a name, a miss and a false alarm. Depending on the context, the cost of one kind of error is different from the cost of another kind of error. So, based on the context, you have to determine some cost. In the case of an airplane in a war situation and radar, which one is higher, the probability of a false alarm or the probability of a miss? If you've got enemy aircraft in the sky and your radar doesn't detect it because it's missed the plane, is the cost of that kind of error the same as the cost of mistakenly assuming that there's a plane out there and firing up an anti-aircraft missile? Which one? It's much worse to miss one in that case. Yeah, exactly. So depending on the context, the people who make policies on these things have to make those kinds of determinations. So in a lot of problems in more advanced courses, if you ever take a course on random processes, detection and estimation, you will have cost functions associated with each of these outcomes, and the optimization problem then becomes minimizing that cost. And that cost function will depend on the context. So the context of a war situation with radar and aircraft will have a different cost structure. It will give a miss a much higher cost than, say, in this case, where I think I would probably venture to guess, I don't want to go into social policy making or pontificate on that, but a false alarm, I think, in this case is far more devastating to the people involved. Yeah. Okay. Let me just say one thing broadly about what we've been doing. Bayes' theorem is essentially about, in fact, conditional probability in general. It's about revising your prior estimates of the likelihoods of events given observations, measurements, or new information. That's basically what is at the heart of this whole discussion. So, a priori, we might ascribe a 5% likelihood to a person, randomly selected person, being HIV infected. But once new information comes from the test result or test results, then we revise that estimate that we originally had. That's what it's really all about. And the way we do it is by drawing the sample space or identifying what the possible outcomes are, and then based on the information that we get, we prune that sample space to correspond to the case that we have observed or to the measurements that we've made. So, in this case, the two-test example, the pruning is done as soon as I tell you that both tests came positive. Well, then you look at all the possible sample points, and you look at the ones, you get rid of all the other outcomes that don't correspond to the two tests being positive, and you focus on the ones that are, and you rescale all your probabilities so that in your new conditional space, all the probabilities add up to 1. That's what the denominator is. The role of that denominator is simply normalizing everything. The relative probabilities of the events stay the same when you condition on the new information. Okay. I think this is probably a good time to take a little break. And then when we come back, I want to say more about conditional probabilities. And then hopefully near the end of the lecture, I'll get to the union bound so the TAs don't kill me if I don't get there. All right, take a break. Okay. Let's resume. So we've been talking about conditional probability for a couple lectures now, and we defined it last time as this ratio. So the probability that event A occurs given that B has occurred is given by the joint probability of the joint event, scaled or normalized by the probability of the conditioning event. And this is if P of B is greater than 0. Otherwise, it's undefined. Now, there's this notion of independence that I alluded to and we talked about last time in the context of rolling a six-sided die twice. And independence, one way to look at it is that if I give you information about event B having occurred, it does not alter your assessment of the likelihood of A. So in other words, if the probability of A given B is the same as the probability of A, it may as well be that I didn't give you information about B, and we say that A and B are independent. Then we say A and B are independent. Okay, so that's one way to think about independence. Another way is by using the definition of conditional probability, which was probability of A and B over the probability of B. Now we're saying for independent events, this is equal to what? Probability of A. And so the implication is that the probability of A and B is the same as the probability of A times the probability of B. In most contexts, this is the more useful version or the more usable version of our definition of independence. So we say two events A and B are independent if this is true. The probability of their joint event is the product of the individual probabilities. So that's A and B independent. That's what we're going to do. I'm going to ask you a series of questions. I'm just going to frame it as examples. Here's my sample space. I've got event A. I've got event B. I want you to tell your neighbor if events A and B, as I have drawn them, are independent. What's the answer, folks? No? Who says no? Okay, who says yes? No, I don't know is not an answer. So there's a whole bunch of you who are still not answering. That's the whole point of talking to your neighbors, to reach a decisive answer. I'm going to give you 10 more seconds. Okay. One more time. Who says they are not, well, I don't want to do a double negative. Who says they are dependent? Who says they are independent? We're not making progress here, people. Okay, for those of you who said they're dependent, just okay. I'll pick you. Yeah, you know? Yeah. What's your name? No. 2 rows, curly hair. Yeah. Ben.
I would argue that they're dependent because the probability of A and B is clearly 0, but the probability of A and probability of B are both non-zero. Non-zero times non-zero is typically non-zero.
Typically. Probability of A and B is the same as, what is A and B?
Intersection of A and B,
Which is the empty set. And what do we know about the probability of the empty set? It is 0. Now the way I've drawn it, A has a non-zero probability, a positive probability, and B has a positive probability. And this is not equal to the probability of A times the probability of B. Because that's on the right-hand side, you've got a strictly positive probability. You can look at it also in the other formulation. If I tell you that B has happened, what can you tell me about the probability that A happens? A can't happen if B has happened, right? So this number is 0, which is not the same as the prior probability of A. I introduced a new term, prior probability. That means the unconditional probability. Probability of A given B is sometimes called a posterior probability, meaning that it's your assessment after some information has been given to you or after you've made some measurement. Yeah?
By definition, we're saying that A cannot happen if B happens.
That's right.
That's our definition, but A can still happen in the same outcome space, right? Like what prevents B?
Not if I have told you that B has already happened. If I've told you that B has already happened, then this is your new sample. This is your new sample space. This is your conditional sample space. Now you're dealing with all the elements that are sitting in B. And so you have to rescale all your probabilities so that the probability in that new conditional space, purple here, sums to 1. Okay? All right. Now let's do another one. What if I have B? Let's make that A. I make that B. And I ask you, are A and B independent? In particular, what is the probability of A given B? Darn, I gave away the answer. It's not the only way to argue it, but are A and B independent? Altogether? No. Because if I tell you B has happened, what can you tell me about whether A has happened or not? It has. So what should I put on the right-hand side? 1. If B has happened, you know for sure A has happened because B is a subset of A. Okay? Now, let's extend this idea of... Any questions on what we've done? Okay. Let's extend this idea of independence to the independence, or in some books you will see mutual independence, of a set of events A1 through AN. So if we tell you or ask you about the independence of some number of events, you can assume that we're talking about mutual independence in the sense that I'm about to define for you. So we say A1 through AN are independent or mutually independent if the probability of their intersection is equal to what? Well, actually, it's not just any intersection. It's not the intersection of all of them. It's the intersection over some set of I. So here, S is for every S, a subset of 1, 2, to n. In other words, I take any grouping of these events, I look at the intersection, I compute the probability, and that probability must be what? What do you think? Inspired by the n equals 2 case. Let's see what this says. This says intersection of A1, let's say, or maybe A2. Well, actually, that's going to mess up the... It's some intersection of a combination of these. What should that be? What was it in the 2 case? A1 and A2 are independent if probability of A1 intersect A2 is what? Probability of A1 times A2. So what should I put here? Probability of AI. It's the product of these AIs, right? So if I have, let's say, A1, A2, A3, any combination of these events, when I look at their intersection, the probability of that intersection is the product of the probabilities. Let's do it actually for the case 3. Let me go back to this. So let's say, so here's an example. N equals 3. So I've got 3 events, A1, A2, and A3. I say A1, A2, and A3 are in the... Don't want that. A1, A2, and A3 are independent if the probability of A1 and A2 is equal to what? Probability of? Everybody. A1 times the probability of A2. What else do I need to test? A2 and A3 must also be the product. And what else? A1 and A3 must be the product of the individual ones. And what else? A1 and A2 and A3 is the product of the individual ones. Yeah? No. You need all of them. I'm going to show you an example. So, yeah. It's a definition, so you can treat it as if and only if. It is not enough for you to show the last equality. It is not enough for you to show even all 3 of the first equalities. Notice I'm sidestepping subsets of size 1. Is an event A independent of event A? If I had more time, I'd go into it. But it turns out an event is independent of itself if and only if its probability is either 0 or 1. So aside from that, those cases, every event is highly dependent on itself. So if I tell you what's the probability of A given that A has happened, you get 1. Or you get for any other set that doesn't have an a priori probability of 1. But let's skip that for now. So let's go to our rolling of the dice example. I had a sample space 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I have a red die and I have a green die. By the way, the question that I was asked, let me actually give it a name. These three here talk about pairwise independence. If you show all three of these, all you've shown is that the events in your set are pairwise independent. Pairwise independence does not imply mutual independence. So this is actually one place where using the word mutual is helpful, because then you can distinguish the two situations. Mutual independence always implies pairwise independence, but the other direction does not hold. And we'll see that here. So I've got two rolls of a roll of a red die and a green die. And let's see. And I say the event yellow is, whoops, come on. Oh, it's not giving me the highlighter. This is the event yellow, right there. And it is the probability that the red comes out 1. Okay? What is that probability? Quickly. 1/6. Then I have the probability that this purple one, that the green one has come 1. That's 1/6. Okay? And I'm going to define another event. What is this color here? What is it? Sapphire, whatever. Blue. This one is the event that the red and the green gave me 7. What's that probability? 1/6. We did this all last time. Okay. Now, all kinds of things can happen. Two events might be unconditionally independent, and as soon as I condition on a particular other event, they become dependent. So, do you agree that, let's see if I can fit, okay, here we go. Do you agree that R1 and G1 are independent? The red die came 1, the green die came 1. The probability of their intersection is what? 1 over? And is that equal to the product of the individual ones? Yes. Equals P of R1, P of G1. Okay? Now, what if I tell you that event R plus G has happened equals 7? R plus G equals 7. So, I tell you that I rolled a red die, rolled a green die, the sum of the two numbers was 7. Is the event that the first die came out 1 independent of the event that the green one came out 1? Talk to your neighbor. By the way, just to give you some formulation, let me give you a quick definition of conditionally independent events. We say A and B are conditionally independent if whatever we said before for unconditional probabilities now holds in our conditional universe. So this must be equal to what times what? When I didn't condition on C, what was the definition? Probability of A and B is probability of A times probability of B. So now I've conditioned my universe to C. So what must that product be? A given C times B given C. If this is true in my new universe, all you're doing is that you're going from one universe to another universe. If this is true, then we say that A and B are independent conditioned on C. Or they are conditionally independent given C has happened. Okay? So now let's go back to my question earlier. Are R1 and G1 conditionally independent? Yes or no? No. Because why? Yeah, if I tell you the sum of the two rolls is 7, it cannot possibly be that each of them was a 1. Notice in my conditional sample space, now I'm living in this universe of blue. What happened to the yellow and the purple once I conditioned on blue? They've now become mutually exclusive. And we talked about mutually exclusive sets. They are as dependent as they get. So in my conditioned sample space, which is the blue, the yellow and the purple become disjoint. And they become dependent. Okay? So two events can be independent before conditioning and become highly dependent after conditioning. The reverse of this can also happen. Two events can be dependent before conditioning, and after conditioning they become independent. And you'll have opportunity to see examples of these as we go forward. Okay. Let me now talk about, there's one other important situation that I wanted to talk about, which was raised earlier, which is that pairwise independence does not imply mutual independence. So, let's say my events are, so here, pairwise. This is very important. Independence does not imply mutual independence. The reverse is true. Mutual independence, because by definition, this is by definition, implies pairwise, because one of those subsets of the integers 1 through n is the size 2 subsets, pairwise independence. So let's look at this one for a moment. Okay? So we've said already that red and green both being 1 is 1 over 36, and this is the probability of red being 1 times green being 1. What can you say about probability that the sum of the two is 7 and the red came out 1? Let's go back to our diagram. What's the probability that the sum was 7 and the red one came 1? What's the answer? 1 over 36. Is that the product of the two events? This cell is what I'm looking at, right? The sum is 7 and red came 1. That probability is 1 over 36. The probability of yellow is 1/6. The probability of blue is 1/6. The probability of their intersection is 1 over 36. So are they independent? Yes. Okay, good. Now I can do the same. So this is 1 over 36 equals probability that the sum was 7 times the probability that this one was 1. And what happens and we can say the same thing about, by symmetry, we can say the same thing about G1. This is also S7 times G1. But what is the probability that you have red 1 and G1 and the sum 7? What did we say about that? 0. Zilch. And that's not the product because you can't have all of them, right? You can't have the first one come out 1, the second one come out 1, and the sum be 7. That's not possible. So this is not the same as the product of the individual ones. So this is an example of the kinds of traps you can fall into if you're not careful. Pairwise independence does not imply mutual independence of events. Okay. Now, before we end, I want to get into the union bound so you can at least handle some of the problems that will come your way in discussion and homework 9. Union bound has different names depending on whom you ask. It's also called Boole's inequality. And it's also called the subadditivity property. And it's quite an intuitive inequality. It simply says, well, let's write it in the two set case. If I have, what did we say about the probability of the union of A and B? It's the probability of A, and then what? Help me out here, people. Probability of B minus the probability of A intersect B. Now you know that the probability of any event is always non-negative, so this simply means that the probability of the union of A and B is always less than or equal to the probability of A and the probability of B. This is simply the union bound or the Boole's inequality or the subadditivity property articulated for the case where you have only two sets. Okay? The generalization of this is for n sets. In fact, you can do a countably infinite set of sets. So if you have sets A1 through AN, the probability of A1 union A2 union all the way to AN is always less than or equal to the sum of the individual probabilities. You can prove this using induction. There are also other cool ways of proving it. There is also a nice way of proving it without induction. I think I'll actually I can do it without induction for you still and be able to do an example for you. So let's look at the non-inductive proof. Gosh, these people are loud. So I'm going to do it for the case of 3 sets. Let's say I have 3 sets here. A1, A2, and A3. Okay? Instead of looking at the probability of their union of these 3 sets, I'm going to define a new set of sets that happen to be mutually exclusive because I know how to apply the probability of a union of mutually exclusive sets to that combination. So here's what I'm going to do. I'm going to define a set B1 which is equal to A1. There you go. Okay? Here's my A1. I'm going to start with the first indexed set. I'm going to define my set B2 as A2 minus A1. That would be this green region here, right? A2 minus A1. Everybody with me? I'm going to define my B3 as A3 minus A1 minus A2, minus everything that has come to pass in terms of indices. And that would be what? This portion here. Right? Do you agree that these B's as I've defined, and if I have more sets, A sub n, I would just define all these B's exactly the same way. For every new index, I subtract from that A sub k, whatever it is, all the previous areas. Do you agree that B1 union B2 union B3 is the same as A1 union A2 union A3? Okay, the way by construction, right? I constructed these B's in this way. And we've also ensured, by the way we constructed these sets, that they are mutually exclusive. So, the probability of B1 union B2 union B3 is the same as the probability of A1 union A2 union A3. And I know what about these? It's equal to what? The sum of, because B1, B2, B3 are mutually exclusive, these are what? Probability of B1 and what? Probability of B2 and probability of B3, right? And do you agree that B1 is a subset of A1? That B2 is a subset of A2 and B3 is a subset of A3? Do you agree? The way we constructed them? Yes or no? Yes. Okay. So, what can we say about the probability of B1 relative to the probability of B3? Remember 2 lectures ago? It's less than or equal to. This one is less than or equal to. And the same here. So the sum, so then here you have your inequality. Less than or equal to the sum of all the A1 probabilities. Okay, so that's the proof. Unfortunately, we didn't get to the example. I'll do it next time. But you'll see plenty in discussion. So that's essentially the union bound, and it's got some interesting applications. All right. Have a great spring break.